right, hello everyone. Let's start. So today is lecture 12 of Advanced Topics in Quantum Information Theory. And first of all, thanks to everyone who filled in the surveys of the evaluation of the course. In general, people seem to be very happy with the course so far, which makes us very happy. So thanks also to Ralph and Nuria, who've been doing such a great job with the course. There was like two main pieces of criticism. One was that lecture notes sometimes are a bit behind, and they will be behind. They'll be there before the exam, but not probably, for my part, not before the end of the semester. Next year, when we give the course again, we'll have the lecture notes from the beginning. The other criticism, which you're completely right about, is that some of the videos on YouTube, there's like the videos of the students there, which is not so nice. So we are now working on blurring out your faces. It might take a week or so until this is done, but it will be done. Okay, and I think the videos from now on, they only have my video there. Good, so last time we talked about modeling measurements as physical processes, as some interaction between a measurement device and the system to be measured. And then we talked about replacing the counterfactuals and these kind of paradoxes like Hardy's with measurements by different agents. We'll recap this a bit. And today what we'll try to do is to replace these counterfactuals with instead very weak measurements, so very weak couplings to a pointer, and see what we can deduce from there. And we'll also talk a little bit about pre- and post-selection paradoxes more generally. Okay, so now this is the beginning of trying to give some structure to all these paradoxes that we've been talking about. And let's take it very slow and see how far we get with this. Okay, so a long time ago, meaning probably 2 or 3 weeks ago, we started talking about these, sorry, Hardy paradox. Sorry, I'm looking for my notes. Yeah, and there, okay. Where we talked about this kind of timeline, where we prepare. So if this is time going there, at some initial point, we prepare some state on some system S. At some later point, we measured some observable. Some observables, let's say B, which we only looked at perfectly projective, nice observables. So it was of this sort. BL is just the label for the observable. For example, this could be the X. And then kind of it's like a basis measure. And we also looked in cases where we post-selected in some outcome. On outcome L, right? And then we wondered about what would have happened if here we had measured another observable. So what if we a different observable, right? And the idea was to find kind of chains of reasoning that led to contradictions. So we looked at the pigeon example, and we looked at the Hardy paradox in different forms, right? Then last week, we kind of replaced the setting where here this is an hypothetical measurement that was not performed, what we sometimes call counterfactual measurements, with an actual measurement. So we saw that a measurement can be implemented by some interaction between a system to be measured and some measurement device, M, pointer. In this case, we said, well, this measurement device actually represents the whole agent that is measuring, say Alice is measuring it. And here inside this system, M, we put all of our memory. Okay, so we did this unitary, which in our case, we simplified to just a C naught, right? And then we say, okay, she did this, and now someone else is going to come from the outside. So Ursula came from the outside and made a measurement on like this whole system, right? So she performed the second measurement. And what she did then was to reason about, well, not directly about what Alice had thought at that time, but we had a more complex setting where she thought about what he thought, that she thought, and so on. Okay. So this is what we did last week. Today we'll do something different, which is a weak measurement. So here we have this interaction, but it's not such a strong interaction as a C0. In a C0, then this system is perfectly correlated with this. And now we look at a case where they're just very weakly correlated. Then we're going to perform the second measurement on system B, on system S. So this is the measurement with the post-selecting. And if the post-selecting is successful, which means that if we're happy with the outcome, then we do a measurement on the pointer, on this measurement device, and we look at the statistics here as kind of a shortcut or a way to simulate what would have happened if here we had measured this observable A directly, right? So the idea is that this unitary here kind of implements A. Okay, so how do we do this? Let's just recap what we did last week. So we talked about measurements as physical processes. So we start with some initial state of system S, in which we want to measure this observable. And if this is a pure state, we can just write it out, just expand it in the basis of this observable, right? So like perfectly projective, nice observable. And then we have the measurement device, which for the case of weak measurements is convenient if it's a continuous system. It doesn't need to be, but we can simulate it with a discrete system that has many levels, has a high dimension, but let's do a continuous system. So we expand it in the X basis and it has a wave function, which is just the coefficients for different states. And then we saw that there is some kind of interaction between the two, okay, which is the observable that we want to observe in the first system and something on the second system. I put C here because we used B for something else. So this will later be the momentum. Okay, and we can in principle put some constant there. Right, just make this interaction stronger or weaker. For example, in the experiment where we couple the spin to Stern-Gerlach experiment, where you couple the spin of the electron to the position, you could tune the strength of your magnetic field such that the final impact on the screen, so the position that you'll measure of the pointer, instead of being very separated for spin up and spin down, they're actually very close together. Okay, so this is just some constant that we can tune later. That's it. And then we saw that if we apply this interaction for some time t on our initial state, then we get this kind of correlation between the two states, where here is the eigenvalue of the observable. Here's the eigenstate. Here's the coefficient. So it's the overlap of our initial state of the system with this outcome. And there's our operator on the measurement device. So then if we call this whole state phi k on the measurement device, then we will look at specific examples, right? And the specific example we looked at first was when this object here was just a momentum observable, okay, which you can expand in the momentum basis like so on M. And then we saw that this leads to a shift in the position of the pointer, right? Such that if you look at the final state, so at this final state, and you trace out the system, then what is left is just this this incoherent mixture of the pointer settings. Okay. Now, depending on how peaked the initial state was, and on the value of this time t and constant g, then we had more or less overlap between the peaks corresponding to different outcomes, right? So what's here is the position x of the pointer at the end. And overall, what we have is the probability of finding the pointer at a given x, which will be something like this, right? Where this peak corresponds to outcome A0, and this peak corresponds to outcome A1 on the system. Okay. So how do we do this? How do we then actually measure? We didn't get to this. But how we then actually get the outcome of our measurement that we wanted to do on the system is by now doing a measurement that's a bit stronger on the pointer itself, right? So we did this interaction. Let me write it here. We start with the system and the measurement device. We did this weak interaction for a while. Now we leave the system alone, and what we'll do is measure the pointer. And because now we're thinking of the pointer as a 1D system, we're going to measure the position. And let's say that we can measure the position precisely, so we do a perfect X measurement on M, which in reality is not what's happening, right? So then let's see what the results are in this case. So if we measure, let's say, for example, we just want to know what is the average position of the pointer at the end. Okay, so we have this. This is the final distribution according to us, and we want to see what the position is. So we saw that the state rho m, rho m was the sum over k of alpha k squared. Okay. And now the average of observable x for the state rho m, observable x on m, well, that's just trace of x rho m, which we can write out as just trace of x sum over k by k. And then because the trace is linear, we can bring this sum over k to the outside. And we're just left with trace of x. That's right. Well, now this is just the average position for each of the states psi k, right, by definition. So let's move to the next page. And I notice now that on YouTube you cannot see all of this diagram. So yeah. Okay. Good. So now we have sum over k. So this is the average x on rho m, sum over k, alpha k of this x for each of the states phi k on m. So let's find out what this is. Well, this very simply, again, so this is psi k x psi k, and now we expand these states in the x basis. You know that this observable x is just like p, it's just this. And now we expand this state in the x basis, and there'll be enough inner products that are just a delta function that the result is just, as in quantum mechanics 1, given by the wave function square multiplied by the value of the observable at that point. But what was this? Well, this we saw that this was the x, and now this was just the original wave function shifted by this value, right? T, okay, right. And now we can make a change of variable just by saying like, I mean, just by going from, let me write it here. If we call this x prime, then you do the change of variable and so on, and we obtain, well, that this is just the average value of x for our initial state, phi 0, minus this thing, right? Or plus this thing. Plus this thing. Good. Plus this thing. Minus this thing. Plus this thing. I don't know. We'll find out. I think it's plus. That's right, plus. Okay. Now, this is the state that we chose initially, right? So we could have chosen any state of the pointer, and unless we're feeling particularly like masochist, we'll choose some nice state centered around 0 to make our life easier later on, right? So this can be 0 by design. For example, the original state could have been just a Gaussian centered around 0. Okay, that's a very beautiful Gaussian there. Okay, good. So then we just replace this here and we get what? Sum over k, k squared, and now we get this t ak. Okay, these are the experimental parameters, this gamma and this t, which again we can tune, right? So gamma was the strength of the interaction and t is the time during which we'll let it interact. Okay, and we can keep this value the same if you just increase one, then decrease the other. So let's just call this whole thing g. So then we're left with g sum over k squared ak. But what is this that we observed here? Well, this is just g times the average of the observable if we had measured it directly on the initial state of the system. If we just made a strong measurement of the observable on the system, then the average value would be this. And the way to see this again is by seeing because sorry, psi, yes, psi. Well, this is sum over k, psi ak, psi ak, but this, sorry, this was the wrong way around. Up. ak psi, and now ak the coefficient. But this was, by definition, this coefficient's lambda k, so this here will be, sorry, alpha k, so this will be alpha k star, right? So, which you can see from going back from the first time we defined the state, we just expand it in this basis. So this coefficient here is just the overlap. This is just, okay, right? Good. So what does this tell us? Well, it tells us that we can get some information from this measurement, right? So by let me just highlight the important result. This is the important result. By looking at the final position of the pointer on average, we get some information about the average value of the observable if you had measured it directly on the system with like a perfect measurement. Okay, but now we can ask, well, what happens now that we have post-selection? Okay, so let's write down the whole procedure again. So we start with, let's see, now with post-selection. We start with psi on S and the phi 0 on the measurement device, on our pointer. We let them interact with this U, where U is E, 2 minus I T H bar. Then we're going to measure some measurement B here on the system. And then, like I said, later on, we're going to measure here our pointer in the X spaces. Now, if this is all that we're doing, then in order to know the measurement outcomes here, we don't need to care about what happens here, right? Because quantum mechanics is local in this way that in order to know the outcome or the probabilities for outcome of a measurement there, it doesn't matter what I'm doing over on the other side, right? Even if this was a Bell experiment where here there's a fully entangled pair, if I just care about the outcomes of my measurement in the X or Z basis, I don't need to care what Alice over there is doing to her state. But the difference is that now we're post-selecting, which means what? So it means that we look at all the outcomes of this measurement here, and we, after doing everything, we only select the rounds in which we got the outcome that we wanted. Okay. And this now is a highly non-local thing, because it's like Alice and I share a Bell state, and yes, if I just look at my probability distribution is independent of what Alice is doing. But if now I condition on Alice having gotten outcome 0, for example, in the Z basis, then my distribution changes, right? So if we had, for example, if we had 0, 0 plus 1, 1 over square root of 2, right? And now I measure on the Z basis the second system. Then if this is the probability and these are the two outcomes, 0 or 1, and this is the probability of X and this is X, then the probability would be like 1/2, right? So I make 100 experiments, and after 100 experiments, I have more or less 50 zeros and 50 ones. But now Alice tells me, look, discard rounds 1, 7, 4, 3, which are all the rounds in which she did not get outcome 0. Okay. Then what's left is a very skewed distribution here, which will be a distribution where I always get 0, right? Because now we're conditioning on Alice only getting 0. So that's the same of what will happen here. So what happens is that if you consider all the outcomes, then we had this kind of distribution, right? But now if you condition on this measurement here, only getting some outcomes, then the things that survive are going to be very odd. So they could be, for example, just a little bit of the tail here, where the average will be something like very out of the normal distribution. Okay. So again, this is like, well, if you've seen this movie Unbreakable, for example, so there we have someone who's looking for a superhero, and this person, without spoiling, looks at many many disasters, right? And if you just look at many disasters, the chances of finding a superhero is very small. But now if you post-select in the disasters where everybody died except one person, then the odds that this person is a superhero is very, very high, right? So that's the idea. Because we're going to discard so much of what's happening up here, then the result here is going to be a very skewed distribution. Okay. So now let's just see what the state of the pointer is after the measurement with post-selection. And I warn you now that we'll not go through all the calculations explicitly. I leave some for the tutorials. Okay, so what's the state of pointer? After post-selection. And let's call this state, it's the state at time t star when the outcome of the measurement was L. Okay, so t star, let's say it's this time here. Okay, so we measure this observable L, this observable B, and we condition on the outcome L, so that corresponds to this. So then what we have here is BL on S, nothing happened on M. This is one thing that happened. There was this unitary before on S and M, and there was the initial state sin S tensor by 0 on M, right? And of course, we need to normalize the state. So let's just call this is the probability of getting L in this measurement, right? Okay, because we need to renormalize the state at the end. So we're selecting only some part of the outcomes. And then to get a proper state, then we need to multiply by the probability that here we got the outcome we wanted. Okay, and we don't need to worry about what this is for now. So we get 1 over this probability of L, the L over S, identity on M. And now here we have this state that we saw before, sum over K, alpha K. Okay, and let's keep it general, so this could still be the alpha K on the measurement device. Good. So this gives us probability of L, sum over K, and now we have just alpha K. Let's leave it there for a while. BL AK. And this is a number, and this is by K. Okay. Now, remember what we said about this outcome. So this is just AK in the initial state, right? And this is also just a number. Okay. So let's just rewrite this. Probability of L, which we don't know yet. Okay. BL, AK, AK. Initial state. Okay, good. And now we ask, look, this is a pure state because, again, because we post-selected in the same way that if we post-selected on Alice always getting 0, then we also get a pure state on Bob's side here, right? Instead of the mixed state. Good. So now the question is, what can we observe by measuring this? What information can we get about this hypothetical measurement, this perfect measurement A that we wanted to do. Okay. All right, so then let's write just first what the average position is, and then we'll see two cases. So of M. So this X for the final state, so for this phi of L, well, we get to sandwich the state. Yep. So get one of the probability of L. I missed the square root. Yes. So attention, I missed the square root here all over. Check. Okay, good. And now we get two sums on K and K prime. And now we get kind of all of these terms double, one for K and one for K prime. And then we'll get the sandwich of this with our observable. So let's see. We have the L, AK, AK psi. Then we get AK prime, BL, and then we get psi AK prime. And this whole thing is multiplied by now. So I'll put times phi of K prime X phi of K. Well, and now we need to compute this thing here. And this now depends on the strength of the value. Okay, so now this on essentially on phi 0 and on this constant G, which was the coupling strength and the time of the measurement together, right? So let's look at two cases. First, we look at the case of the strong measurement. So I'll put it in a new slide. So if we have a strong measurement, what does this mean? This means that we have this kind of peaks like the pointer is really separated, right? So this would be your wave function of K, and this would be the K prime of X, right? So they don't overlap. Okay, so in this case, let's say that if you multiply the two wave functions, this is 0 unless they are the same, they correspond to the same outcome. You never get this perfectly, but you can kind of approximate if these tails are very small. So this is approximately delta K prime, and then this. Yeah. So in this case, if we want to compute this thing, this expectation value, then again, you'll end up with these two integrals, x of for K prime, and the wave function for K multiplied by X, right? But then this is just we just replace it with this thing here. And we get just the x square of x, okay? And this is just, again, the average x up for some state, for just one of the outcomes. So here, if we have this case, then times this delta that carries over. And this delta is very useful because then when you go back here, and yes, all of this sums simplify because you only care about the case where the cases are the same. And then you just have that this is the complex conjugate of that, so you get the absolute value, and this is the complex conjugate of that, so you get the absolute value again. So in this case, you get that the final result for the final state of the pointers. So this was, what did I call it? Phi time t star outcome L. Then you get just 1 over this probability of L we carry around, sum over K. The average value of X for this psi K, which we know. And then, sorry, phi K, and then this BL AK square. AK, and this overlap with initial state square. Now, this, we know that this is just G times AK, right? Okay, so that's the case in the case where we have a strong measurement. Right? And this corresponds to kind of the same statistics as if we had gone there, made this measurement, compute the probabilities, and then do the second measurement. Now, what happens when we have a weak measurement, and what does this mean? This means that our final state of the pointer looks like a bit like this, like, you know, this is without the post-selection. There was like very little shift in the wave function. And with the post-selection, what we can do is take this general state and then kind of approximate for the case where G is very, very small. Okay, so if G is very, very small, and phi 0 is, for example, a Gaussian function, centered in 0, and then we can do essentially expand terms in here, do some approximations, and this is something that either you did already in the tutorial or you will do in the tutorial. So I will not go into detail here, but then I will when I write down the lecture notes, I will put it all down. The point is that the derivation itself is not super necessary here. But what matters is that the final state that we get of the pointer, so this state, let me copy it. this state can actually be approximated by a Gaussian. This is approximately some new wave function x, where this wave function of x is a Gaussian. So I think these are the right normalization constants. If not, doesn't matter. But what matters is here, what's up here. So x minus g. This is a constant that will define AW square over 4 delta square. So if you look at the position, delta is just the initial uncertainty of the pointer that you had in your original Gaussian. And this is the new average position. So x for this final state is going to be g AW. And what is this AW? This AW is going to be what is called the weak value of the thing, which is BL A I over BL initial state. Now, before we go to the break, let me just try to explain more or less what these terms are. So this is what we call the weak value. And again, if we did not get how we got there, it's really, we take this state, we expand this thing here. This we leave as they are because they will show up there. And so we expand this state and then we make this approximation. And then we get that the final result is a Gaussian. This AW, it's a complex number divided by another complex number, so it doesn't need to be a real number. But of course, that if then we measure the position, then we get this, the modulo square. And what are these terms? So this is kind of the probability of getting outcome L if we had not made any measurement, right? If the circuit had been just this, just prepare psi and now measure here the B observable on system S without anything in between, then this would give us the square root of the probability of getting outcome L, right? Whereas this, what is this? So this is this term here. You can see it as, well, maybe the best way to do it is BL sum over K, AK, AK, psi. Okay, and you can see this as the probability of getting BL given that you perform the measurement in between, right? So this corresponds to this circuit. I prepared phi, I measured A, sorry, I really measured A, and then I get a quantum state, the post-measurement state, and now on this state, I measure B. Okay. And because I'm missing here an AK. Okay, so this is the probability of getting L when we measured A in between. Right? So it's kind of the probability of getting L given that I made the measurement in between, a strong measurement in between, and the probability of getting L if I had not made that measurement. Okay? So now what you do in the tutorial is kind of explore properties of this of this weak value and then use it to derive some results when you apply it to Hardy's experiment in particular. Okay. So after the break, we'll move on to something else because I want you to actually derive this expression in the tutorials before we can talk more about this. So we'll go for a break now. If we have questions, ask now. Otherwise, I'll come back 5 minutes before.
I have a question regarding the weak value. Do you hear me?
Yeah. Yes.
So if our initial function psi has no overlap with PL, then the weak value diverges. Does that mean that the average x value that we measure is infinite since it's proportional to the weak value? So when BL overlap with psi becomes 0, then AV is
with your
infinite.
Yeah.
How does that relate to the x measurement then at the end post-selected on measuring BL?
Okay. So I think the thing on top might also diverge there in that case. Okay, the answer is that there's an elegant answer and I don't remember it right now.
Okay. Shall I ask on Moodle?
Yeah. Yes.
Again, okay.
Yes, you can ask on Moodle and I'll answer it over the next few days. So I just saw now that there was a comment 10 minutes ago about one of the sides should have a K prime as a...
But yeah, that was something small. That was on this...
Where is it?
Like the upper part.
Is it before this?
No, not the next one. The approximation there. On the slide previously.
Sorry, the previous one?
Yeah, this one. One of the K's should have a prime.
Here. There you go.
Yeah.
There you go. Yeah. That's it, right? Yeah, that's the only case. Okay, good. Yes, but the idea is that these things can indeed... I mean... Look, in that case, by the way... Actually, I have maybe an answer for Florian. So, two options. If this term here is 0, right? Either your measurement is not super weak, and then you cannot use this approximation, so this would not hold, right? Or suppose it's super weak, then you're never in this situation. You never see this, right? If it's super weak, then it's like the measurement that you actually performed is very similar to just doing this circuit of applying the measurement directly, right? So you almost never, it's like you're hypo-selecting on an impossible outcome. You never see this.
Yeah, okay,
and if you do see it, it's because it's not really 0. But then yes, then you do see a peak very far away, but you need to make many more experiments in order to be able to post-select sufficient cases for this, right?
Yeah. Okay, so because I was thinking before that this observable A could mix the eigenspaces and then it could create an overlap between psi and BL. But in that case, if it's a weak measurement, then this unitary we apply it only weakly generates this, say, overlap.
Yes, exactly.
And in this approximation,
yes,
say intuitively it makes sense that everything should stay well defined.
Yeah, that's the idea. Yes.
Okay, great, thanks.
Okay, good. We will play more with weak measurements, I think, in the tutorial, not so much in the main course. I'll make a break now. Okay, let's continue. Okay, so this is the preliminary conclusion here is that we derived how this weak value come to be. Okay? We saw that it has some relation about, so by the way, this is given by the average position of our pointer at the end, and you can see it as like an indication of what's the probability that we got this outcome, given that we measure this thing in between, divided by the probability of having gotten this outcome if we had not measured this thing in between. As such, by using Bayes' rule, we can relate it to this kind of counterfactual measurements. But now this is like one more piece in our machinery that we're building up. We're going to let it rest for now so that you can practice in the tutorials how to derive these things, how to apply them to Hardy's paradox. And now we're going to see kind of a more general way to phrase this, this kind of counterintuitive scenarios, which then later on we will bring together the weak measurements as kind of a witness of such behavior. Okay. So essentially what we'll conclude is that whenever we see the pointer as somewhere strange, is because we are in the presence of one of these paradoxes. Okay, but we're going to let it rest for now, and I'm sorry that the two parts of the lecture are a bit disconnected today. Okay. So let's rewind. Let's go back to this original setting where we prepared some state psi, and then here we could make a measurement A, and then later we make a measurement B, and we post-select on an outcome BL, which, so we don't have to write BL all the time, let's just call this phi, okay? So now we're back to the idea of one single system, and what we'll try to do is kind of formalize some set of rules for when does this thing have a strange behavior, and then what does this tell us about quantum mechanics. And then later on, we will come back to the physical setting where we actually, this thing is an entanglement with a physical pointer, and we'll see what we see here can inform whether we are in one of these strange situations or not. Okay. So then if we go back here and we want to think about what's the probability of getting some outcome K here, given that I got this outcome L here at the end, right? Given that I got this outcome phi at the end, that I could post-select successfully in that thing. Well, this is just the probability that, well, you start with your original state, then you made this measurement and you only care about the successful cases, so where you projected into the outcome K that you wanted. So this could be, for example, your AK, and then we made this measurement and we post-selected on this outcome here, right? That's exactly the same. Now we can ask, okay, now what's the probability of having gotten this K given that I post-succeeded, right? So now we're post-select as, given that the post-selection succeeded. We post-selected on getting the right outcome here at the end, L, which is our phi, and now we're asking of this, like how many of this measurements gave me, okay, what's the probability of having gotten K there? And again, this is probability, just applying Bayes' rule. Okay, given this thing divided by the probability of this thing actually succeeding, okay? And now realize that we're in a scenario where we do perform this intermediate measurement. So then what is on top? It's just this phi. Okay. Initial state square. And what's at the bottom? It's very similar to what we just saw before. So it's the sum over all the possible outcomes. So over all the possibilities, right? Of what could have happened there. So of up 5 pi k phi square. And then I can rewrite this, leave the top as it was before. And I can just split it into that case. So, okay. All right. Well, all I did was to expand this projector into this. And then it's like the square of the product is the product of the squares in absolute value. Yep. This thing is called the BL rule after Maharanov and his students who found out, we found out this rule for the probability of getting some measurement in between, given that we pre-select and we post-select, right? So I can add here everywhere that this is all conditioned on having prepared the initial state psi, right? Good. So this is one of the ingredients we need. We need a few more. Find it. Not this. Okay. Good. Okay. So now let's try to formalize the problem. And I'm following a paper by Matt Leifer and Matt Pusey from 2015. Yep. And it will have several ingredients. So the ingredients are this ABL rule. The proof will be some contextuality that we have not talked about yet of quantum mechanics. And the other rule, well, it's just going to be this, let's just call it algebra. Okay, good. So then let's look at the following setting. So the setting is the following. We fix this pre and post selection. So this means we prepare this state. And we measure, and we only keep the statistics of those corresponding to this outcome phi. Yeah. Then for the intermediate measurements, we represent them by projectors. So some projector P, and we only care about, for now, for this result, we only care about binary measurements where you only have two outcomes, the one that corresponds to P and the one that corresponds to identity minus P. So for example, if you have a Z measurement, then PZ is 1, 0, for example, and identity minus PZ is the projector that corresponds to the other outcome, right? That's the example. And okay. And now we're going to expand this to a setting where if we start from such a set of measurements, okay, of binary measurements, and now we're going to assume that we can compose these measurements, right? So this is going to be the case of like in the Hardy experiment, we can compose an X measurement in the first qubit with a Z measurement in the second qubit. Okay. So consider this trick is the smallest set of projectors such that it contains our original measurements. Okay. If it has one projector, then it must have the one corresponding to not getting that outcome, getting the other outcome. And if it has two measurements and they commute, then PQ, then we can consider them together as one measurement. Okay, so let me give example. So say that P is in the Hardy experiment is this. So it's like we measure the first qubit in the Z basis, so that's two projectors. We measure the first qubit in the X basis, that's two projectors. And then we do the same for the second one. Okay, so these are just our raw ingredients. Right? And then what this P thing does is to also include, so I'll not write the whole set of projectors, but it includes all the joint measurements. So it includes, for example, the fact that I can put this one together with this, which corresponds to the outcome of measuring the first qubit in the Z basis, getting outcome 0, and measuring the second in the plus minus basis and getting outcome plus. Okay, so this includes things like for example, etc. But it does not need to include the multiplication of this with this because these are not compatible measurements, right? So essentially what it does is if you have a set of measurements, if you have an original set of measurements and you just take every two that are compatible and you create a new measurement out of this. Okay, it's just saying if I can do this independently and they commute, then I can do them together, which is the same rule as we have in quantum theory to consider what are compatible measurements, right? So that's what this thing here does. It's just to expand this, the original set of projectors there. Okay. All right. So then we need one more ingredient, which is the probability function. Function where we write that the probability of some projector P, and this is a bit unfortunate of my side because both start with P. This is what we mean by the probability of getting this P given the pre-selection and the post-selection, which is exactly this thing that we saw before. Right. This ABS rule that we saw before. Let me just copy it. That's maybe a bit easier. Okay. Okay. Right. So remember, each P corresponds to an outcome. It's like I could have a K here. Okay. Good. So this here. P. And I'm sorry, I think there's a mistake here. Yeah, so here we sum over only the let me do this in writing. So we sum over all measurement outcomes, but there's only two measurement outcomes, right? So it's the P or 1 minus P. So we get I think let's get back to this later. Yes, no, that's it. Yeah, okay. And then we ask, does this probability function behave normally? Okay, is it well behaved? And that's so. And let's just give it a different name. Let's call this f of P. Just well-behaved f of P is one that satisfies the following conditions. One, so it's a probability, so it belongs between 0 and 1. 2, well, if our projector is the identity, then the probability should be 1. And if our projector is nothing, then the probability should be 0, right? This is for all P. And the third one is that it behaves normally when we have more than, when we have two outcomes. So if PQ, if these two things commute, then the probability of this outcome, P plus Q minus PQ equals F P Q minus F of PQ. Okay. Now, I'll show you in one simple example how this behaves strangely for one paradox that we have not seen yet. And then you'll do in the tutorial next week how it behaves for the Hardy paradox that we've seen a million times. Okay, so this way you get exposed to yet one more paradox. So this is kind of the critical thing. Okay. And so we say that if these three conditions are not satisfied, then we say we have a logical pre and post selection paradox. Okay, so example. And this is what's called the three-box paradox. Yeah. So now we've seen paradoxes that had 2 qubits. So that's a 4-level, 4-state system overall. But turns out that that's not the smallest system where we can find paradoxes. So you can find paradoxes already with just 1 qubit. So only 3 states. Okay. So let's say that the Hilbert space is a span of 3 states. And it's very similar to the pigeon paradox. Okay. So we have state 1, 2, and 3. And we can think of them as asking, where is the particle? Is it in box number 1, number 2, or number 3? Okay. And now we do a pre-selection. So that is square root of 3. And we prepare just like very similar to what we did with the pigeons. And then at the end of the game, we measure it in a different basis, and we post-select only on this outcome, which is 1 plus 2 minus 3. Okay, and now we ask, well, what could be the intermediate measurement? So let's suppose that the intermediate measurement is asking, so again, remember that this is the beginning, we prepare this. At the end, we post-select on that, and then in the middle, we're going to do something. Okay, so we're going to do some measurement M with some projectors P. Okay, and this measurement is going to be just, is it in state 1 or not? So let's say, P1 is just 1, 1, and of course the identity minus P1 is just 2, 2 plus 3, 3. Okay. All right. Then it turns out, if you do the math, that the probability of finding it in box 1 is actually 1. So the probability of P1 with this is 1. And you can compute it directly by just doing these overlaps with this state. So this is just psi and okay. So this is 1, but it turns out the probability of, if we had instead looked, is it in state 2, is it in the second box, then the probability would also be 1. Okay, so I'm missing something here. Sorry. missing the squares. Identity minus P1 and the other state, and this is all square. Okay. Okay, so if you measure this one, and I recommend you do, then the probability of getting P2 is also going to be 1. Okay. Which means that, I mean, the kind of classical view at this is that if at this point we had looked in the first box, we'd found the ball there deterministically. But if you had looked in the second box, it would also have been there deterministically. So what does this mean? Does it mean it was in both boxes at once? It's just strange. Okay. Of course, that this is us trying to like kind of plaster classical intuition into this. But now let's see how it looks like in our new with our rules. Okay, so with these rules, and we'll see that it breaks this condition. Okay. So in this case, and here I'll just show it, and then so I'll show the results, and then in the tutorial you'll actually prove it. So okay. So in this case, we have that f of this projector P1. This was P1. As we saw, the probability of finding it in this state is 1. The probability of the other one, was also 1. And then do they commute or do they not commute? Yes, they commute, right? So P1, P2 is P2, P1, which is 0, because this is just 1, 1, 2, 2, and that's 0, but you get the same thing here, right? You get the same thing on this side. Okay. So then we can apply this rule. So we look at this thing. Okay. So this is f of P1 plus P2 minus P1, P2. Well, that's f of one plus 2, 2 minus 0. And on the other hand, on the right-hand side, we had f of P1 plus f of P2 minus f of PQ. Okay, and this turns out to be 1, like we saw, plus 1 minus 0. Right? But that's 2, and that violates rule number 1. Right? So it can never not together with this, because this is a valid projector. And together this would violate rule number 1, because this can never be a probability that is between 0 and 1. Right? Okay. So this was an application of that rule of this rule to a new paradox that we did not know yet. And what we want to try to get a feeling of is like, does this really capture all of these paradoxes that we've been looking at? Okay, so I will stop here because I think it's a good point for you to try to think whether it does apply to it or not before we try to explore what conditions should an experimental setting satisfy in order for this to be violated. Okay? So what the homework will be for next week is going to be apply these conditions to the Hardy paradox and try to see that indeed they are not all satisfied at once. Okay? And then you can apply the same conditions to the Putin experiment and they will not all be satisfied at once. Okay? Then the next thing we'll do will be from here, we will try to prove when are these not all satisfied. We relate it to this phenomenon of quantum contextuality, which is a generalization of non-locality. And then at the very end, then we'll come back to the weak values and see that the weak values are actually a good witness for when this last condition is not satisfied. So that's that is it for this week, actually. So we're going to stop here and we'll continue again next week. And I have for some reason, there's a question on YouTube. Right, so there's a question on YouTube from the end of the first lecture, and the question is, so the weak measurement does disturb, the system, but it disturbs the system less than a strong measurement. Okay, so of course that there's a trade-off between how much information you get out of it, so how much you can infer about what would happen if you do the real measurement, and how much you disturb it, so how much you can later apply the second measurement on top of it. Okay? This is like a whole field of research, and I would like to get into it, but I'm not sure we'll have time for it in the coming lectures. Okay, so we'll see. So what I've done today again was to just give you two ingredients. One ingredient was this weak measurements. The other ingredient is this kind of phrasing of what pre and post selection paradoxes are. You can now go play with both of them, and then in the next lecture we'll start to bring them together. That's all for today. Are there questions? I imagine that'd be.
I have a question regarding the very beginning of the second lecture where you presented the ABS rule.
Yep.
I'm not quite sure whether I managed to follow you regarding these two probabilities you wrote down. So there's the first, and then there's the second line, and
So
what do these probability, or what's the difference between these probabilities on, or say,
okay, so this
level?
Yeah, so this one is the probabilities that, look, I made this measurement. The first measurement, I got a classical outcome and the state that corresponds to it. And then I take that state and I make the second measurement, right? And again, I get some state that I don't care about anymore, and then outcome. Right. So now, what is the probability that I got outcome K here and outcome L there? So this is like, think of it like your classical probabilities of, I do two experiments, what's the probability that I get these two results, right? That's what this thing is. So it's the probability that, given that I prepared initially the state psi, what's the probability that first I got this outcome K, so that's this projection, and then, oh, and there's some things missing, right? There's this projection, and then given that, I project again into this B basis, and I got this outcome L. That's the first one, right? And the second one is just, okay, now what's the probability of getting K? Condition on the fact that I got this outcome L that I wanted at the end. Okay, so that's the difference. So there I need to divide by the probability of getting this outcome L at the end.
Okay. Yeah.
Yeah,
Yeah,
that's
that makes
why.
sense. Yeah.
That's why I need to sum here over everything that could have happened down here, which is getting every possible outcome K of my measurement. So I'd get different states here. And then what's the probability of getting the outcome L here for each of those states? Right, that's why I divide by this. That's just this probability. Yeah.
Okay, yes, that makes a lot of sense. I must have missed at the beginning that the first probability is getting K and then the post-selected phi.
Yes, exactly. Yeah. Yes, so you should interrupt actually when this is not clear. Okay.
Okay. Yeah.
Good. Okay.
Thanks.
Well, there are more questions? So if there's no more questions at this point, then I'll stop here and I'll see you next week.